This is the Linguistics Podcast. Questions or comments can be directed to Twitter at LinguistChris or on WordPress, http://linguistchris.wordpress.com. Hello and welcome to the Linguistics Podcast. My name is Chris, and today our topic is, if your computer could talk, what would it say? I should mention that this is the first episode of the podcast we've had that doesn't just go over introductory linguistics. We will be, of course, using the concepts that were gone over in those first 6 episodes in the rest of the material, but I think it's important that we move on to something a little bit more interesting for those out there who are already somewhat versed in linguistic concepts and the terminology used therein. If you are not well versed, I'm going to remind you to go and listen to episodes 1 through 6. Actually, episodes 2 through 6 really are the important ones, because they cover, just in a nutshell, some of the things that you would have in an introductory linguistics course, and they're important for learning the terminology and the vocabulary that I'm going to be using and talking about some other issues. So today, clearly the topic then is about computational linguistics, and I should also mention that this is not the only computational linguistics podcast that I will have, the only computational linguistics episode I will have, I should say. I'm very interested in the field. I think it's a very sort of up-and-coming field, especially in linguistics where things sometimes have been described as a little bit stagnant in some subfields. Computational linguistics is not stagnant in the least. It's very much of interest to researchers today, and will be for quite some time, I think. It is a complex field, so it includes many issues, some of which are machine translation, speech recognition, speech synthesis, and language modeling. So today what I wanted to do is go over, just very briefly, those 4, what I mean by each one, and then in future episodes I'll go into more detail on some of the issues, probably specifically language modeling, because that's where my primary interest currently is. So, let's start with speech recognition. Now, interestingly enough, speech recognition is probably something that everybody listening to this podcast has used at some point. The reason for that is that often in telephone systems, we find a speech recognition system. So if you call, let's say, I don't know, your telephone provider, and of course you don't get a human being when you first call, you get a computer talking to you. It says something, often a pre-recorded message, and then waits for your input, and you talk to it. Oftentimes you're only saying things like yes, no, sometimes you might say, operator, customer service, something like that. But the computer still sort of figures out what you're saying and directs you to the right place most of the time. Now, I should mention that speech recognition systems, especially those over the telephone, are famously inaccurate, to where you have people screaming at their phone because they're saying, customer service over and over again, and the computer doesn't understand what they're trying to say. And I'll explain why that is also. So, what speech recognition systems like those used over the phone are essentially engineering exercises in pattern matching. And what do I mean by pattern matching? Well, I mean that, first of all, the context of speaking to a computer over the phone is very limited. So there's a limited number of responses that you're expected to make when you're talking to one of these systems over the phone. So possible responses, like I just said, might be yes, no, customer service, operator. Anything outside those responses is not going to be understood. It's not designed to accept input like the weather outside is nice today. If you call your phone company and start talking to their computer system and you say the weather outside is nice today, I guarantee you it will say that it doesn't understand what you're saying, because it's not designed to. It's designed with a very limited context, and limited context is it's a way to increase accuracy in the system. Because if you're pattern matching, you're only looking for sound patterns in certain words. So the word yes versus no, if you were to look at a spectrogram of those words, which is a visual way of looking at sounds and frequency patterns, you would see some sort of visual patterning difference between yes and no. Now, clearly they're about the same length, so you can't really use length effectively, but you can see a frequency difference between yes and no. And you can make a set of patterns of different people saying yes and different people saying no. You make what's called a corpus, which is a body of data, and from that corpus, you can statistically decide whether somebody said yes or no by looking at averages of data within your corpus and matching it up to what the person said. Okay. Now, clearly, the more limited your context, the better. So if you're only two possible inputs were yes and no, then your system would probably be quite accurate because it's only looking for two possibilities. 50-50 chance right off the bat, and if you only have to separate it two ways, you're going to bump your accuracy way up. And most of these systems probably have more than two things that they can listen for. So one being customer service. Of course, with customer service, you can bring in the length of the utterance, but if you say customer service quickly, then you could probably fit it into the same amount of time as saying yes, so on and so forth. These are the sort of things that engineers think about when they're making speech recognition systems. And I say engineers specifically here because traditionally, linguists, I don't think, have been too interested in speech recognition. It is, like I said, an exercise in pattern matching. Perhaps those who are very interested in phonology might be interested in speech recognition, but I don't think it's really the cusp of research in computational linguistics at present. I think the corporate world is very interested in it for obvious reasons, but I'm not sure that it's that interesting in an academic sense. All right, so that's all I'm going to say about speech recognition. I will also mention one more thing about it. Speech recognition in terms of dictation. So these systems, often commercially available systems where you talk to your computer and it writes what you're saying, those are essentially the same sort of system, but the context is much more broad. And oftentimes you'll have to train these sort of systems with the patterns that you yourself make. So they do this by having you speak to the computer. It then builds a corpus based on your own patterns for words it knows it's putting out. So it shows you a word. You say the word to the computer records your voice, checks your patterning, your own patterning for how you say things, and tries to then adapt its built-in corpora of other data to your voice. So essentially it's pattern matching. It's much more involved pattern matching, and obviously the context is much broader, and as a result, oftentimes those dictation systems do not have the kind of accuracy that most people would prefer, although they are getting better as computing power allows for larger and larger sets of data to be used for this sort of statistical pattern matching. Okay. Now, from speech recognition, let's move on to speech synthesis. Now, this is the opposite of speech recognition. This is going the other way, so you want to go from what would essentially be the written word to speech. The computer is actually talking. Now, I should mention that speech synthesis systems actually have been around longer than speech recognition systems. One example I can think of right off the top of my head, a consumer-level speech synthesis system was available. I'm gonna go mid-90s. It might even be earlier than that. On Macintosh. So if you have a Macintosh computer, you know that even way back in System 7, I think, at very least, it may have even been there before then, you had a system that could speak to you. You typed text in some text edit program, and you could say, speak this, and it would speak your text. Now, it's not very good. It sort of sounds very computerized, and still to this day sounds very computerized because it's very much the same system, but nonetheless, it is a speech synthesis system, and they were around much before speech recognition systems really got very accurate. Now, how does speech synthesis work? Well, just as speech recognition deals with patterns in the reverse operation, speech synthesis also deals with patterns. So basically, you have a corpus of phonemic patterns. Okay, so the computer knows what frequencies generally make up phonemes. Then all it has to do is break down the input, the text input, into syllables. Better systems will do this. Some systems don't do this, actually, which is interesting. They break down the input into syllables, then they break those syllables down into phones. So it's basically two operations that they run on the input. And then they generate those phonemic patterns with the proper meter. Okay, so if you have a system that does work with syllables, they generate the proper meter for whatever language they're working on. So in English, if you have a two-syllable word, it's generally stress on the first syllable and de-stress on the second syllable, like the word meter itself is like that, meter. You have the E, gets the stress in meter, which is the first syllable. And if you have a three-syllable word like, apprehend, you get that last syllable stress. Apprehension, So penultimate syllable there. You see these stress patterns that are in English, and the program will be programmed with those stress patterns, so that it can sort of sound more human-like when it's synthesizing the text. Okay, but still, I'm going to say mostly an engineering exercise, because the concept, the linguistic concept behind it, doesn't change. You can improve upon that system without the assistance of a linguist, right? Once you get the concept down. So is it academically interesting at this point? For me, not really. I think both speech recognition and speech synthesis are really for the computer scientist at this point, or the engineer. Not so much for the linguist, but they're still sort of put into computational linguistics, and certainly there is some research that deals with both. Okay, now let me move on to machine translation. Now, machine translation is, again, something that a lot of people have used. This has come, in the last 10 years, it's exploded. Things like Systran, Google Translate, these are all machine translation schemes. Machine translation is a type of natural language processing. So what you do is you type something in English, and in some cases they put a speech recognition system with a machine translation system. So I think Google Translate has something where you can speak to it, and it tries to speak back to you. You should remember that it's actually three systems that are involved there. One is the speech recognition system, which converts to text. Then your text is translated to text in the other language. Then your text in the other language is synthesized with a proper speech synthesis system for that language. So really you do have three systems at play. And so when I say machine translation, I'm talking about the part that actually does the translation, the text-to-text translation. So a system like Google Translate, for example, in a system like that, there's not really any actual natural language processing being done. Systems like this utilize massive amounts of online data. And it's essentially engineering shortcutting. So they're not modeling human language per se, but they're using massive amounts of user-created data to pattern match to existing translations. So again, there's this pattern matching scheme. This sort of statistical approach has dominated computational linguistics, especially in the private sector, for quite some time. And I'm not sure if it's letting up quite yet, but it's a sort of commercially interesting but not really academically interesting pattern matching scheme, and it's done essentially the same way as the speech systems, just with text. So you have massive amounts of text, translated text, and they match pattern to pattern, and there's some underpinning of natural language processing, some more intelligent underpinning that actually is linguistically valid. But the focus of it is to get a quick result with a fair amount of accuracy. Okay, now, I should mention that online translators are also pretty notoriously inaccurate. Unless you're dealing with short, simple, common sentences, they're going to fail, and that is because of their nature. They need, the more common the sentence you put into it, the better the translation in general, because it's a system that's working with a large amount of crowdsourced data. Okay. So if you have something really off the wall and you type it in, it probably won't be right. Or it might sort of fall back onto a more robust natural language processing system. But in general, the focus is a shortcut, an engineering shortcut. Okay. So let's get on to what is academically interesting and linguistically interesting. And that is either principled machine translation, or some will call it language modeling. Language modeling is so called because it was thought of in the late 80s as a way to sort of learn more about what humans are doing when we speak or when we comprehend by modeling human language on a computer. So by programming a computer to think about language in the way that we think humans think about language, is it a viable method? Can the computer understand language and generate language in the same way a human can? It's a pretty powerful concept, really. It's been used for a variety of applications. And one application that I think is coming up is essentially the replacement of all these statistical systems with these more principled systems. of machine translation or language modeling. But how do you go about this? How do you teach a computer human language in a principled way without cutting corners? Well, the first thing you have to understand is the differences between computers and the human brain. So computers at their most basic level are essentially procedural beings. They perform operations in a sequence. Now, I'm not getting into parallel processing or any of these computer scientific issues, but in general, the computers are procedural beings. Now, I'm using procedural here to differentiate between that and declarative. Okay, what a declarative system is a system based on facts and deduction. Okay, formal logic, a deductive system, a declarative system. You declare what facts are, and from the facts, other things can be deduced. Now, it's thought that human language uses a lot of deduction, and that it is, in essence, a declarative system primarily. There are some procedural elements, obviously, as language is, after all, linear, but it seems to be declarative in nature. That's the general consensus. And thus, computers are automatically at a disadvantage, being solely procedural. But there are ways to get around that. And so generally what's done with these principled methods of language modeling is to use a logic language. What a logic language is something like Lisp or Prolog. These are programming languages which are designed to simulate a declarative system. Okay. Now, if you get into programming with Lisp or Prolog, you notice that even though they're supposed to be declarative, there are still some procedural issues that sort of knock on your door as you're trying to make these systems in the way that files are loaded and so on and so forth. So it's not perfect, but it is the closest I think you can get to a declarative system on a computer, and so these methods have become very popular. So how would you do this? Well, you would take and you would list all the ways to make a verb phrase, for example, by rule. And to build a verb phrase, actually, interestingly, it is somewhat procedural. However, to match it with a lexicon, clearly you need a declarative system to handle that. So that's what I'm saying. There are procedural elements to this, but in general it's declarative. So you list by rule the ways to make a verb phrase, you list by rule the ways to make a noun phrase, and then all that you say in this declarative system is that to make a sentence, you put a noun phrase and a verb phrase together. Okay? If you've programmed it correctly, the computer should be able to generate all possible sentences with the lexicon that you give it. Okay? So you declare what is a VP and what is an NP by rule. You declare all items in a lexicon by fact, and it deduces the rest. Okay, so that is the power of a declarative system in terms of language processing. Now, there's a big plus to working in this way, and it is that declarative systems operate in two ways. So let's say you make a declarative system that links sound and meaning. Okay, so the sound that somebody makes when they're speaking, like I'm speaking right now, and the meaning that I'm conveying to you. Now, presumably, when you hear the sound that I'm speaking, your brain takes that sound and breaks it down somehow, and you end up with a meaning that you conceptualize in your head. And then, presumably, when you want to speak, you have some meaning conceptualized in your head, and your brain puts it through some process, and it comes out as sound if you want to speak that meaning, right? Declarative systems work in just that way. So, if you have a link between a sound and meaning, you can give a declarative system the sound, and it will spit out the meaning. Or you can give it the meaning, and it will spit out the sound. Now, why is that such a big plus? Well, it means you get machine translation for free. Okay? So let's assume that you have a system that is built to process the grammar of English. And it's a complete system. Now, such a system I'm not sure exists currently. I would sincerely doubt it. But let's say it does. Let's say you have a system that can completely process English in a principled way. And you have a system that can completely process Swahili in a principled way. Okay? And both of these systems share the same method for representing meaning, because this is another challenge of computational linguistics that I'm not going to go into today, but you have to have some method of notation for meaning. You have to define what does it mean to have a meaning? What does a meaning mean? These sort of weird semantic questions. You have to get some concrete method of notation for those. But if you do, and both your Swahili grammar and your English grammar share that same notation, then you can put a sound into the English side, and it will spit out a meaning. Then you can wrap that meaning into the Swahili side, and it will spit out Swahili text, perfectly translated without the use of any corpora, just with the use of a lexicon on each side. So it's as if you had two human speakers sitting together, and one human speaker said something, and the other speaker translated. It's quite brilliant. I mean, in its simplicity, because it seems so simple. In fact, it's very complex, because you have to worry about things like processing time. How computationally efficient is it to do this type of natural language processing? Can it be done in a realistic amount of time? These sort of things come into play, but when you back up from it, it really does seem quite simple if you have these grammars completed. And working on these grammars and the issues that arise from trying to build these grammars is not only of great interest to researchers, especially researchers interested in artificial intelligence, but it's also a question which is not nearly been answered at all, really. It's sort of both the new frontier and the old frontier. It's interesting because language modeling has been an idea for quite some time now. But because the private sector got so interested in statistical methods, that sort of most of the research focused on those methods. And now that we're getting to the point where computers are getting so fast that an actual deductive declarative system could be used to do these sort of things and do it more accurately in likely the same amount of time, that becomes very enticing for researchers, and certainly for linguists who want to use the same sort of implementation for different applications, because you can tell a lot about how language works if you have to break it down and make it run in a declarative system. So that is principled machine translation and/or language modeling in a nutshell. So does anybody really do that? I mean, I say it's of interest to researchers. Do I have any proof? Well, one thing you can look at is IBM's supercomputer Watson, which just fairly recently in the last couple of years, I believe won Jeopardy. I believe that was its claim to fame, is it won Jeopardy. And it had a natural language processing system built into it, and that natural language processing system, lo and behold, ran on Prolog, a pseudo declarative system ran its natural language processing. Now, granted, it had a limited context. It was designed only to sort of have the answers in form of a question or whatever they have on Jeopardy. It was designed only to understand that. So the context was limited compared to a more robust natural language processing system. But regardless, IBM's supercomputer used Prolog. I should mention a very old programming language and a fairly old method in principle, but still I think the way to go if you want to make a system that really understands what you're saying and can break down language in a meaningful way. Okay? So back to the topic of today's episode. If your computer could talk, what would it say? Well, we've gone over ways that it could talk. You could have a very robust language modeling, natural language processing system using Lisp, Prolog, some other pseudo-declarative system. You could use this and couple it with a speech synthesis system, which works with these phonetic patterns and so on and so forth. And you could have a computer that could not only understand what you're saying, but say something back to you. The question is, what would it say? And the answer is, if left alone, likely nothing. In fact, almost guaranteed that it would say nothing. It will say whatever you want it to say. But what we should not confuse is a talking computer with an intelligent machine. When we break down language into a declarative system, like I've proposed here, we're not making intelligence. certainly people that are interested in artificial intelligence are interested in systems like this because it seems to take it one step closer, because it gives a sort of communicative competence to the machine. But really, we're not adding intelligence to a machine when we do this. All that we're doing is making a machine say what we want it to say and let it understand what we're saying. Now, the applications for that are endless, of course, in terms of computer interfaces, in terms of telephone systems. Imagine if your telephone system was actually a robust system for language processing, where if you told it the weather was nice today, it knew what you meant, and the accuracy was just through the roof because this thing could understand language in the way that a human does. I think that that's not too far in the future that will be the case in these systems, but regardless, left alone, the computer will say nothing, because after all, it is just a computer, and there is still certainly a big difference between a computer and a human, no matter how much language modeling you do. Okay, so that concludes this episode. Next episode might be another computational linguistics topic, or I might try and switch it up a little bit. More likely the latter, I think, just to keep it more interesting. So, as always, I thank you for listening. You can find me on WordPress at linguistchris.wordpress.com, or I welcome questions and comments on Twitter at linguistchris. Thanks again.